Welcome back, everyone. Today, let's start chapter 23. In fact, I think technically the first two sections of this chapter were due, if you will, several days ago. That's partly because when I plan out classes for a normal semester, I'm thinking in terms of the timing of exactly 75-minute blocks, which we don't necessarily have here. That being said, I plan, if at all possible, to get us well past those first two sections today. And so chapter 23 is about carbonyl condensation reactions. To me, this represents the last kind of important reaction that carbonyl-containing compounds undergo. And in order to understand a carbonyl condensation reaction of any type, whether it's an aldol condensation or a Claisen condensation or a mix of the two, whether it's intramolecular or intermolecular, whatever the details may be. In order to understand a carbonyl condensation reaction, there's two very important concepts from past chapters that we absolutely have to have down cold. And one of them is this notion that we addressed even at the very beginning when we were first learning about carbonyl compounds. And I see I've cut off my cranium again. There, that's a little better, just so everyone knows that it's still there. In any case, we said that carbonyl groups, whichever compound they may show up in, are subject to nucleophilic attack, and that's for two reasons. First of all, the carbonyl carbon has a partial plus charge because this is a resonance stabilized species. And the minor contributor to the overall molecular orbital picture shows a plus charge on this carbon atom. So that means that whatever the other two things are that are attached to the carbonyl carbon, whatever they may be, there's going to be a partial plus charge in that carbon. And the other reason is because the oxygen atom is, of course, very much more electronegative than the carbon. And so in the tug of war for these bonded electrons, which we know is exactly what electronegativity is, well, the oxygen's winning. And so that's another reason that the carbon has a partial plus charge on it. So we should expect that nucleophiles will attack carbonyl carbons. We also saw in the previous chapter that enols and enolate ions, especially enolate ions, are very good nucleophiles. And so we expect them to attack various kinds of electrophiles. And oftentimes this will be a primary alkyl halide or tosylate, but it does not have to be. There's other electrophiles as well. And so basically what we're saying is carbonyl-containing compounds are electrophiles, enolates are nucleophiles. And all you need to know to understand carbonyl condensation reactions is that we can combine both of these ideas into one and stipulate that the nucleophile that could be attacking a carbonyl carbon could itself very well be the enolate ion of another carbonyl species. And that's all we mean by a carbonyl condensation reaction. It's another nucleophilic acyl addition reaction or substitution reaction, depending, in which the nucleophile is an enolate. That's it. If we understand that, then we can understand the Aldol and Claisen condensations and all the various spin-off reactions of that. So that's the main idea that we have to have down cold before we understand this. As I think ahead to other things that are going to be helpful, another concept from Organic 1, specifically in chapter 11, that's going to be helpful, is the idea of the E1CB mechanism, since we're going to see some E1CB dehydration reactions coming up pretty soon. So that's something, if you've forgotten about that mechanism and you need to review it, please go back and review that in chapter 11. It's going to be pretty important coming up. Now, an aldol reaction, like we just said, is just a nucleophilic addition reaction to an aldehyde or ketone in which the nucleophile is an enolate, period. That's all there is to it. Generally, these are done in basic solution. It's possible to carry them out in acidic medium. And we've already talked about the differences in terms of how we think about reactions in acidic medium and how we think about reactions in basic medium, or alkaline. But the mechanism will be analogous in either case. Usually, though, this occurs in alkaline solution, and you may get a chance to practice the acid solution case in OWL or some book problems as well, but both can occur. So let's start off with the simplest possible aldol condensation we can get, which is just the combining of two of the same aldehyde or ketone. Let's even make it just acetaldehyde, which is just a simple 2-carbon aldehyde. And in the aldol condensation, we can combine 2 acetaldehyde molecules to get the product that you see over here. And the mechanism is very straightforward. There's nothing here we haven't seen before. We're already at the point in the semester where I'm going to be hard-pressed to come up with something that will surprise you entirely. So let's say that we mix these up with aqueous hydroxide, and let's just throw in some ethanol just to make sure everything dissolves properly. I don't know how well these molecules will all dissolve just in aqueous phase. So often you'll add a co-solvent that'll just make everything dissolve better. Bearing in mind, though, that water is a little bit more acidic than ethanol. And when I say a little bit, we're talking in pKa terms. So the units are logarithmic, right? So when we say, so it looks a little more acidic. Water might be 1 or 2 pKa units more acidic than most aliphatic alcohols. And so really that means water is 10 or 100 times as acidic as an aliphatic alcohol such as ethanol. But be that as it may, we know we're in base because we're told that here. We're told that we have aqueous hydroxide. That tells us that we need to use the hydroxide ion as our base. And it won't always be hydroxide. So we don't memorize that OH minus goes here. It might not, right? We make that decision at the time. It's not something that we've memorized ahead of time. This could just as easily have been sodium ethoxide in ethanol. And in that case, we would use an ethoxide ion here. So whatever it is that we're given is what we will go ahead and use. So hydroxide ion will pull off the slightly acidic proton, alpha to the carbonyl in acetaldehyde. We saw that happening in chapter 22. And we get the enolate. And we can draw the enolate this way. We could also just as easily, when pulling off the proton, put the electron pair onto the carbon and show that as a carbanion. That's fine too. It's just the other resonance form. That's yet another case out of many that we've seen of not only will I not take off points, but I won't even notice. It's just another way of drawing the same thing. So that means that you need to practice until you see them as the same thing, not as 2 different things, and are comfortable with the concept of enolates being a resonance stabilized species. Anyway, all we're going to do instead of some nucleophile like an amine or an alcohol or a Grignard reagent, instead of all of those types of nucleophiles, our nucleophile is simply going to be the enolate ion of acetaldehyde, and that will attack another acetaldehyde molecule that has not yet been deprotonated. And so initially you will get this alkoxide ion shown here. We need to get a neutral product, so that means we need to put a proton onto this oxygen. And so again, when we look at what we're given, the most acidic species around happens to be water. That might not always be the case. So again, we don't memorize that H2O goes here. That's not something pre-memorized. That's something we make that decision at the time that we're writing the mechanism. And anyway, once you've done that, then you get the expected initial aldol adduct. Now, as it turns out, this is not the whole story. It turns out that this type of beta hydroxy ketone or aldehyde is pretty unstable, and in a lot of cases, it's pretty hard to isolate. You have to be very careful, keep everything very cold, don't let even a breath of acid get anywhere near it. And in such cases, you might be able to isolate simple initial aldol adducts like that. But I would say the majority of the time, at least 85–90% of the time, maybe more, in fact, this is not what we wind up isolating. And I understand that students are uncomfortable with terms like usually, right? We like terms like always or never. But I have to tell you the truth. I can't give you an always here. This type of compound is not something that we never isolate. Sometimes we will. I think you'll always be given enough information to tell. I will say that if compounds like this are heated at all, even gently, or if you're told that H3O plus is added, if you're told that there's an acidic workup step, which sometimes there will be, you will never be able to isolate things like this. And as we'll see in just a moment, in fact, sometimes even if we don't heat or add acid, we still won't be able to prevent a dehydration reaction from happening. So let's take a look at that. Over here, we've got another example of a simple aldol reaction. Here we're treating cyclohexanone with methoxide ion and methanol. So see if you can work out that mechanism on your own. Notice we're not given water here. So we need to be careful that we show that we don't use water molecules in our mechanism. But other than that, the mechanism is exactly analogous. So that would be good practice for you, getting from this molecule to this initial adduct. And in this case, I don't think it would even matter if we added acid. Certainly, if we heated it at the end, that will make the reaction much faster. And certainly, if we did add acid, that will also prevent us from isolating this hydroxyketone. Instead, what happens is an E1CB reaction. And that E1CB reaction, remember, all E reactions, E1, E2, E1CB, these are all elimination reactions. And what we're going to eliminate in this case is water. So as soon as we get to this product, and again, that mechanism would be something that would be worth your while working out. If you want to come to office hours sometime and show me your work, I'll be happy to tell you if you've done it correctly or not. But in any case, this species is going to react further. So we still have the methoxide ion around. That will pull off this fairly acidic proton that's next to a carbonyl. So that's how we know that this proton is acidic. And we will get the enolate. And you can draw the enolate this way, or again, you can draw it by putting the electrons in the carbon-hydrogen bond onto the carbon atom and draw that enolate as a carbanion. Totally acceptable. It's just a different way of showing the same thing, but it is the same thing. It might be easier for you to see that this is an E1CB reaction if you put the minus charge in carbon. Because when we went over the E1CB reaction, we said that we generate a carbanion first. And no wonder that we do so here, because now this proton is especially acidic, being next to a carbonyl. But whichever resonance form you use, in the next step, this anion collapses and kicks out hydroxide as a leaving group. Now, normally hydroxide is a pretty terrible leaving group. But when we look at what we're given, we see that there's an alkaline solution. I expect that when you see a salt of an alkoxide ion, you may be given CH3ONa, you may be given CH3O minus. I expect you to understand that that's a strongly basic anion, so we're under alkaline conditions. And under such conditions, we can lose hydroxide as a leaving group. Not under acidic conditions. Never in acidic conditions. Alkaline conditions, you can justify it. You can rationalize it. Anyway, notice what we get in that case. We get, and this explains why this reaction usually happens so readily. What you wind up getting always, is a carbon-carbon double bond conjugated to the carbonyl. And way back in chapter 11 or 12, I guess 12 or something like that, we talked about how conjugated pi bonds are especially stable compared to isolated pi bonds. So like I said, some gentle heating of the reaction mixture, and I doubt very much you'll even wind up isolating any of this hydroxy species. I think you would get this conjugated, unsaturated enone, let's say. In fact, in this particular case, not only is this double bond conjugated to the ketone, it's also tetrasubstituted. And way back in chapter 7, last term, we went over how the more substituted a carbon-carbon double bond is, other things being equal, the more stable the species is. So I would say for that reason, and also by virtue of this double bond being conjugated to the carbonyl, that's why this product is much lower energy than the hydroxy species. And so forming the dehydrated compound is generally quite favorable. And all you need to do is have one or more phenyl groups around, aromatic rings. And in cases like that, even if you don't heat it, even if you're not given that it's heated, even if you're not given that H3O plus is added, you can't even isolate that initial adduct. That's going to undergo dehydration and it cannot be prevented. And so maybe we'll end with this example here, which is to say that we'll start with acetophenone. We get the initial adduct here, and that will very rapidly and spontaneously dehydrate to give this unconjugated species, where now the double bond is conjugated not only to the carbonyl, but also all the way through to both benzene rings. In other words, all three of these carbons in between the two benzene rings are sp2 hybridized. And for that reason, there's no way you could stop this dehydration even if you wanted to. So if you want to stop the video before we go into the mechanism, we'll end with this mechanism. If you want to stop it for a moment and try to work out that mechanism on your own, you may certainly do that. So now, if you've unfrozen me, so to speak, the mechanism would look something like this. In this case, we're told that we've got aqueous hydroxide and ethanol. So again, I think the ethanol is just a co-solvent just to help things dissolve better. The first step, again, is deprotonation, alpha to the carbonyl. There's only one type of hydrogen there that we can do that with. Remember, there's no alpha proton off the benzene ring. So we get our enolate. Again, we could draw the enolate using either of the two resonance forms. Both are perfectly acceptable. But if we draw it with this resonance form, we show the enolate attacking another molecule of acetophenone. And then we get this anion once again, just like before. Again, just like before, we're going to protonate this oxygen with whatever we're given that's the most acidic. In this case, the most acidic species is water. And so we put that proton on the oxygen, we get a neutral species, as you see over here. And now comes the E1CB dehydration step. And again, I think in this case, you would not be able to prevent it from happening even if you wanted to. I think even if you kept things cold, I think even if you didn't add acid, it would still spontaneously dehydrate. Because this OH group is the only thing in the way of that fully conjugated system, which represents a drastic lowering in energy, a very, very stable species. And so the first step is going to be our base. In this case, we're given hydroxide, pulling off that proton again. And you can draw the enolate either way, either with the minus charge in oxygen or with the minus charge in carbon. If you draw it on carbon, then it will look a little bit more like what we did in chapter 11, maybe. But either way, this anion is going to collapse and kick out hydroxide as the leaving group. And again, under basic conditions, and most especially when the resulting elimination results in an extended conjugated pi system, hydroxide ion, though not normally a really great leaving group, is good enough in this situation. And so we get this, again, fully conjugated species. And I'm pretty confident that the compound shown here will be the major product by far, maybe even the exclusive one. One could imagine that you could also get the phenyl group over here and the methyl group. In other words, the other one, well, let me see here. So as we have this, I guess that would be the E stereoisomer. And it may be possible that you will get a little bit of the Z stereoisomer, but I doubt there'd be very much at all, if any, because I would expect that the larger benzene ring would be more stable if further away from this large benzoyl group. You would want the smaller of the two groups, methyl or phenyl, to be cis to that group. So that, I think, is a good place to stop. And we'll now get into some variations on the Aldol reaction in our next video. So we'll see you then.